To finish up power series, I want to look at a few minor things, and one thing that's often of use, the binomial theorem. So if you think about this infinite series, 1 plus x squared plus x cubed, and so on and so forth, this is a geometric series. The first term, the a, would be 1, and the number that you multiply a term by to get the next term is x. So it costs me nothing to say this infinite series converges if absolute value of x is less than 1 and diverges otherwise. I don't even need to check the endpoints because of what we know about geometric series. On the other hand, we also know how to actually add up a convergent geometric series. It is a over 1 minus r. So 1 plus x squared and so on and so forth is 1 over 1 minus x, as long as absolute of x is less than 1. Having dealt with that sort of thing before, of course, absolute of x being less than 1 means that x is between -1 and +1. If you take this same formula and replace letter x with negative of x, instead of 1 over 1 minus x, you'll have 1 over 1 minus the negative of x. And in this series, every place that I see an x, I'm just going to write down negative x instead. If the power on the x is even, for instance, negative x times negative x, the minus signs will cancel out, and I'll have, for that term, for instance, plus x squared. If the power on the negative x is odd, though, I'll have an extra negative sign left over after I cancel out whatever can be canceled out. So my series is going to be 1 over 1 plus x is 1 minus x plus x squared minus x cubed, and so on. This will work if absolute value of negative x is less than 1, but the absolute value of negative x is the same as absolute value of x. We get back our -1 to +1 range for our convergence here. It's important to understand this. These two formulas are true only for the specified range of x values. So for example, make x 5. 1 over 1 plus 5 is a perfectly good number. It's 1 over 6. But this infinite series doesn't converge at x equals 5. So you can't just say that these two things are always true no matter what x is. It's only true for x's between -1 and +1. If a, b, and c are constants, it's easy now to expand a function that looks like a over b plus cx about any particular center d that you'd care to use. For example, I want to expand 5 over 7 plus 9x about x equal 1. If I had a 1 here instead of a 7, then this would make me think of those formulas that we just mentioned a moment ago. There is a problem, though. I want to center my power series at x equal 1, which means I need to have x minus 1s in the power series, and there's no x minus 1 in this. It's easy to fix that up, though. X is x minus 1 plus 1. If you multiply that out and simplify it, you get 5 over 16 plus 9 multiplied by x minus 1. So the good news is I've got the x minus 1 in the picture now. The bad news is I don't like that 16, but that too is not a problem. While I'm at it, I'll factor the 5 out too. Factor 5 out on top and 16 out on the bottom, and you'll have 1 plus 9 over 16 times x minus 1 remaining 1 over 1 plus something. We know a power series for that. It's 1 minus the something plus the something squared minus the something cubed, and so on and so forth, which, after rearranging the algebra a little bit, this is an actual power series now. It's a sum of constants times positive whole number powers of x minus c, the c being 1 in this case. This converges if the thing that we talked about previously is less than 1 in absolute value. So I'm going to get absolute convergence when this happens. 9 over 16 times x minus 1 has to be between -1 and +1. Multiply through by 16, divide by 9, add 1 to everything. 5 over 7 plus 9x is this infinite series, that infinite series, if x is between -7/9 and 23/9. We can sometimes use facts that we already know to figure things out. For example, everybody knows that the derivative of arctan x is 1 over 1 plus x squared. That means that arctan x, in turn, must be an antiderivative of 1 over 1 plus x squared. And we have a way of writing series for things that look like 1 over 1 plus something. It's our plan that we got from the geometric series. This will converge when the absolute value of the something is less than 1. Since the something here is x squared, I'm going to have 1 minus the something, x squared, plus the square of x squared minus the cube of x squared, and so on and so forth. That would be 1 minus x squared plus x to the 4th minus x to the 6th, and so on. The absolute x squared less than 1, if you look at the graph of y equal x squared and ask yourself, where is the y coordinate less than 1? That will be from x equals -1 to x equals +1. This is the range of x values for which I'm going to get absolute convergence. Now that we know that, we can wave our hands and say absolute convergence, treat it like a giant polynomial, and integrate it one term at a time. And I find out that arctan of x has this for a power series. With the one little addition, I've got to figure out what the constant of integration is. We know what arctan of 0 is. It's supposed to be 0. So I'm supposed to get 0 for an answer when I put x equals 0 in my series. If you do that, though, all the terms in the series are 0, and it turns out that the constant of integration itself must be 0. The series that we integrated to get this result was a geometric series. But this series, the answer, the series expansion for the arctan function, is not geometric. So we really ought to check for convergence at the endpoints. Also, notice that the arctan function is defined for all real numbers, but that series need not converge for all real numbers. In fact, it doesn't converge outside the interval from -1 to +1. So one should be careful about how you use these things. Based on what we've just said, if I asked you to find a power series for this function, that would now be very easy. You would use the 1 over 1 plus something formula, with the something being x squared, and just write it out. What about this? They're not the same. In the first one, the one that we know how to deal with, on the bottom of the fraction, you square the x and then add 1 in. And in this one, you add 1 and x together and then square the result. That is not one of these 1 over 1 plus something problems. There's several ways we could go about getting a power series for this, but one is to be tricky. This statement is true. You can check it yourself. You can do the quotient rule or a variety of other Calc 1 techniques, but it turns out that 1 over the square of 1 plus x is the negative of the derivative of 1 over 1 plus x. This is true for all x values except x equal -1, where these formulas don't even make any sense. This is true, but how is it useful to us? I know how to do a series for 1 over 1 plus x. 1 over the square of 1 plus x is the negative of the derivative of 1 over 1 plus x, and then write out the series expansion for that, which is valid for x between -1 and +1. 1 over 1 plus x quantity squared is, after I bring the negative sign inside, 1 minus 2x plus 3x squared minus 4x cubed, and so on, which you can write in summation notation this way. Sometimes in textbooks and on tests, somebody will say that, and then you're supposed to find a power series for this. They're telling you how to do it. You're going to take some simple series that you know all about and basically differentiate it. Next, I'd like to talk about binomial series. If you have a number k and it's a positive integer, positive whole number, then the expression 1 plus x raised to the k power is a polynomial. For example, 1 plus x to the first power is what you think it is. 1 plus x quantity squared is 1 plus 2x plus x squared. 1 plus x cubed is 1 plus 3x plus 3x squared plus x cubed, and so on. On the other hand, if k is not a positive whole number, then 1 plus x to the k power is not a polynomial. For example, if the k were equal to a half, you would have square root of 1 plus x, which is definitely not a polynomial. That doesn't even make sense if x is negative and bigger in magnitude than 1. 1 plus x to the -1/3 power is 1 over cube root 1 plus x, which again is definitely not a polynomial because it doesn't even make sense when x is -1. What we want to do is try to develop a method to calculate power series for 1 plus x raised to some constant k power. It is not of interest to us to look at k being a positive whole number because those are polynomials. I'm thinking of building up a Maclaurin series for this function. So I'm going to write down f of x is 1 plus x to the k power. The derivative of that is k times 1 plus x to the next lower power times the derivative of 1 plus x, which is 1, so I'm not going to bother writing the 1 down. The second derivative is k times k minus 1 times 1 plus x to the k minus 2 power. The third derivative is k times k minus 1 times k minus 2 times 1 plus x to the k minus 3 power. This is going to be enough to show me what the pattern is. My constant term is going to be 1. The first derivative is going to be k. The second derivative is k times k minus 1. The third derivative is k times k minus 1 times k minus 2. I think it's probably clear that the next derivative is going to be k times k minus 1 times k minus 2 times k minus 3. So the constant term is going to be 1. All of these derivatives are going to have a number of factors. The number of factors is the same as the index of the derivative. Third derivative, 1, 2, 3. Second derivative, 1, 2. First derivative, 1. I'm going to have a certain number of factors. They are going to be multiplied together. They're going to start at k, whatever k is, and then k minus 1 and k minus 2 and k minus 3, and so on and so forth. If you use the ratio test on such a series, it turns out to be kind of messy, but the conclusion that you draw is that the series is going to converge for x's or the thing, whatever it might be, between -1 and +1. A purist will check the endpoints as well. For my example, I want to look at k equals -1. We're going to calculate 1 plus x raised to the -1/2 power, k is -1/2, that is, which is 1 over square root 1 plus x. I'm just going to write out a few terms here. Based on what we just said, all I have to do is to stick k equals -1/2 into this formula every place where k appears. So if you do that and simplify the result, you get, for the first 3 terms of the series, 1 minus 1/2 x plus 3/8 x squared minus 5 over 16 x cubed. If we needed more terms, we could get them in the same way that we got these. I'm going to use a symbol other than x here for reasons that'll become clear in a moment. 1 over square root of 1 plus something is 1 minus 1/2 times whatever the something is, plus 3/8 times the something squared, minus 5 over 16 times the cube of the something. And this expression will be valid if the something is between -1 and +1. When Isaac Newton did his work, one of the things that he talked about was kinetic energy. This is energy that an object has by virtue of its motion. If you have an object of mass m moving with speed v, v is short for velocity, the amount of energy that the object has because of its motion is called the kinetic energy, and it's 1/2 times the mass of the object times the speed squared. In 1905, the special theory of relativity was published, and there were many issues and concerns, but after a great deal of work, Einstein came to the conclusion that the kinetic energy of a moving object ought to be mc squared times 1 over square root 1 minus v squared over c squared minus 1, where m again is the mass of the object, v is its speed, and c is the speed of light. When you have a successful physical theory that's replaced by a better one later, the new theory has to give you the same answers that you were getting from the old theory in the circumstances where the old theory worked well. If that's not true, the new theory is inconsistent with observation and is no good. So, at least in our everyday circumstances, this somehow has to basically turn into that. And that's not obvious at all. It would be interesting also to see how different these two theories are in some everyday situation. And that'll give us a clue as to whether or not we ought to see all of these relativistic time dilation and length contraction and new formulas for the energy. So what we're going to do is we're going to take our series expansion for 1 over square root of 1 plus something, and the something is going to be the negative of v squared over c squared. I'm only going to write out the first 3 terms here because that's enough to tell me what I want to know. I have to do some squaring. I have to fix the signs up, but this reduces down to the first 3 terms at least, to 1 plus 1/2 v squared over c squared plus 3/8 v to the 4th over c to the 4th, where remember c is the speed of light. I'm going to write down that Einstein formula for the kinetic energy, except instead of writing the 1 over radical part, I'm going to use my power series instead. A miracle happens. The ones cancel out. So this means, at least to the order of approximation that we're looking at here, this means that Einstein says the energy ought to be mc squared times this quantity plus that quantity, and if we wanted, we could look at higher order terms. So use the distributive law to multiply through by the mc squared, and a miracle happens. Using these first 3 terms in the series expansion to a high degree of approximation, as long as v isn't very big compared to the speed of light, the energy is 1/2 mv squared plus this term, 3/8 m v to the 4th over c squared. That is Isaac Newton's formula for the kinetic energy. And to the lowest order approximation, this is how different the relativity energy is from the Newtonian energy. So if v is small compared to the speed of light, which it is in our everyday lives, this term is going to be microscopic, and all you're going to see is the 1/2 mv squared. So things are as they should be. To be clear on this, if the mass of the object was 1 kilogram and it was moving at 100 meters per second, then Isaac Newton says the kinetic energy should be 5,000 joules. How different is this from the relativity answer? The speed of light is 3 times 10 to the 8 meters per second. So I'm going to have to calculate 3/8 times 1, that's the mass, times 100 to the 4th power, which sounds big, until you realize you're going to divide it by 9 times 10 to the 16 power. After doing it on my calculator, this is how different the relativity prediction is from the Newtonian prediction. For a mass of 1 kilogram moving at 100 meters per second, This is so tiny, it's probably not measurable. These effects only get important when the speed becomes a substantial fraction of the speed of light. I think I'll conclude the discussion of power series with this. In the remaining time, we will talk about some topics out of Chapter 10,